In this video, we solve an example of discrete-time LTI systems in the frequency domain and time domain. In this question, the frequency response of an LTI system is given, and the input in time domain is also given, and we are asked to find the output of this LTI system in time domain. First, we need to review a few points. The first point is that in LTI system with impulse response Hn, if the input is in the form of a times e to the power of j omega n, then the output will be the same input multiplied by h e to the power of j omega. The second point is that e to the power of j theta can be written as cosine theta plus j sine theta. We have also used this in previous videos, and I have put the links to those videos up there. The third point, which is obtained from the second point, is that cosine theta can be written as 1/2 of e to the power of j theta plus 1/2 of e to the power of minus j theta. Now let's solve the question. First, based on the first point, we write the input as 1/2 of e to the power of jpn over 2 plus 1/2 of e to the power of minus jpn over 2. Now, using the first point, we can write yn as 1/2 of e to the power of jpn over 2 multiplied by h e to the power of jp over 2 plus 1/2 of e to the power of minus jpn over 2 multiplied by h e to the power of minus jp over 2. Now, in order to obtain yn, we need to compute h at e to the power of jp over 2 and h at e to the power of minus jp over 2. But to make the calculation simpler, we first rewrite e to the power of minus j omega minus p over 4 as e to the power of jp over 4 multiplied by e to the power of minus j omega. Therefore, h at frequencies of p over 2 and minus p over 2 is written as shown in the figure. Now we need to compute the values of e to the power of minus jp, minus j2p, jp and j2p, and then substitute them. To compute this, we use the second point. For example, if we set theta equal to p, e to the power of jp can be written as cosine p plus j sine p. Sine p is 0 and cosine p is minus 1. The result is minus 1. Or if we set theta equal to minus 2p, e to the power of minus j2p becomes cosine minus 2p plus j sine minus 2p. Since sine minus 2p is 0 and cosine minus 2p is 1, the result is 1. In the same way, we compute the other two cases as well and substitute them into the frequency response. The result inside the parentheses in both cases becomes equal to 8. Now, by substituting omega equal to p over 2 into the frequency response, h at e to the power of jp over 2 is written in the following form. We replace every omega with p over 2. Similarly, by substituting omega equal to minus p over 2 into the frequency response, h at e to the power of minus jp over 2 is also obtained in the following form. Now, by substituting these values of h into the equation, we can write yn. Now, we simplify yn. We factor out 8 times e to the power of jp over 4. From the first part, 1/2 of e to the power of jp over 2n minus p over 2 remains, and from the second part, 1/2 of e to the power of minus jp over 2n minus p over 2 remains. Now, using the first point, we can write this in terms of a cosine function. Finally, yn is written as 8 e to the power of jp over 4 times cosine of p over 2n minus p over 2. This was an example of discrete time LTI systems in the frequency domain and time domain that we solved together. If this video was useful, follow the other videos on the channel as well.